So yeah, I'm Johannes. I'm here to present RETBLEED, Arbitrary Speculative Code Execution, work carried out by me and my professor, Kaveh Razavi. We are from the ComSec group, ETH Zurich. So yeah, branch target injection on return instructions undermines some of our defenses, and so that allows like an unprivileged attacker to, they can break kernel ASLR, they can just dump privileged memory from the kernel. So that's of course a problem. So I hope you agree with that. So this instruction maybe you have seen. This is x86 in the AT&T syntax, which nobody really likes. But this is interesting because it's an indirect branch, and it has this nice property that it can have multiple different branch targets depending on the state of the machine. And I say the state of the machine because I'm talking about the speculative branch target that it gets executed before the register is actually potentially known. So a few years ago, researchers found that they can actually influence this indirect branch to make it execute code from some other location where it's not supposed to execute under the transiently then, so under speculation. And this is Spectre with using branch target injection then. So that's of course not very good because we have a lot of these branches in the kernel, mostly indirect calls of course, but yeah, we have lots of these. So there were discussions on how to mitigate this back in 2018. And they came up with this smart idea that, so this instruction is bad, so let's just get rid of this instruction, and we can use returns instead, because returns are essentially, they are like semantically, they do an indirect jump. They are essentially indirect jump used with a pop from the stack. So with this, they built a construct called a retpoline. So this is what we're using in many of our kernels. And they have these similar properties. They have multiple different targets, branch target, and depending on the state of the machine or where you come from in the control flow. So we were wondering if we could do the same on returns, and that's why I'm here today, because we can do branch target injection on top of return instructions. So in these Spectre attacks, they are usually like, they are made of 3 ingredients. There's a speculation primitive. In our case, there's a return. And this is in the execution domain of the victim then. So, and the attacker would choose a return where there is like some interesting information available, like some secret pointer, and also usually some shared memory pointer. And they use this then, so here they would hijack the speculative control flow and take it to something that we refer to as a disclosure gadget. And here then, this secret is being dereferenced and then used in a secret-dependent access in this shared memory buffer. And this allows the attacker then in his own execution domain to infer what the secret was by just accessing this and measuring how fast they can access it. So they will find what it has been recently accessed because it's going to be a bit faster. So the question is, so we're not going to focus on these two, mostly the speculation primitive. So the question is, how can we do this on returns? Because as many of us know, returns have a dedicated prediction mechanism. So they usually go over the return stack buffer or the RSB. So on Intel, we have this thing, but it has like a limited size. So if you have like a deep call stack, like with the function A, calling function B, calling function C, and so on, it's going to be all fine as we go deeper into the call stack. But at some point, obviously, this is going to get full. And what happens then? Well, then we start like replacing older entries then. And this is still all fine, so when we return from this deep call stack, we just use these RSB entries, we return fast. But at some point, because the call stack is deeper than the number of returns that we have in, return targets that we have in the RSB, we're going to have this state where we don't have the RSB is empty. So at that state, the CPU on Intel would fall back to an RSB alternative predictor. And we find that this is actually a branch target buffer, and this is also the one that has been hijacked for the Spectre that we know. So on AMD, they also have an RSB. However, there it works a little bit differently. So if the position of these returns collides with an indirect branch, so they will get the same BTB index, which I'm going to talk about soon. The AMD predictor is just going to go into use the branch target buffer entry here. So in summary, that means that on Intel, return behaves like indirect jump when the RSB is empty, and we can get to that with a deep call stack. On AMD, the return behaves like an indirect jump if there is a bit-to-bit prediction for this location. So, and this we can get by training with an indirect branch. So we want to show that this is actually a security issue. So with that, we want to, as an unprivileged user, leak information from the kernel then. And for that, we need to have a few things. So we need to know how to poison the BTB at the right location. We need to have a vulnerable return in the kernel. And then we need to inject a branch target in the kernel from user space. So these three we're going to look at a little bit. We call this cross-privileged branch target injection. So this BTB thing is providing the branch prediction unit, the BPU, with the predictions, the predicted targets, so that this indirect jump can now choose the right branch target to use here. And it chooses the entry from taking into account the history that you took to get to this indirect branch, and also the program counter here. So with these two, you can form a BTB index, and let's just select the right entry here then. So each of these cells here then represents like a branch target. So what an attacker would like to do, they would like to find some history and or some program counter such that it turns into the same index and therefore overrides this BTB entry. So this is the poisoning or collision. So this is known on Intel since the old Spectre paper, but we were looking at this on AMD, and we found that there we only need to take into account the last branch destination and the program counter. And so the last branch destination, you can think of the beginning of a basic block, and then the program counter is actually where the branch source, the next branch source is. So that's like a basic block, so we think of it like that. And so in order to find like a collision, then we just create an attacker's basic block that is the same. We just flip some bit of the original address and we get it at a new location. And then we just try around until we get a collision. And eventually, we find this, if we flip 2 or more bits, we can actually get collisions that follows this combinational logic. And this is all in the paper, so please have a look if you're interested in that. So next, we need to find like a vulnerable return in the kernel. So we want to make a syscall that leads to a deep call stack in the kernel so that we can do this branch target injection. So to find this, we use the Linux testing project. It has a test suite for syscalls. It has all these test cases, and for each of these test cases, we use ftrace to create the function graphs that we can later traverse and find locations where we have this RSB to BTB fallback. So, and then we have this list of locations, and then we go over those again, and we do some kind of poor man's taint tracking in order to find like what registers or memory that we control at this location. So in Intel, we could find like with this test suite, we could find like 1,000 vulnerable returns like this. However, in many of these cases, we didn't have like control over a full registers. Often we just had control over a user space pointer. However, if we dereferenced, we went like one indirection extra, we would find that we have control over buffer contents, like a message that you pass in like a send message syscall or something like this. So this is what we're using on Intel. On AMD, all returns are vulnerable, so we could just select one of our choice. We choose mmap, for example, where we control 6 registers, which is great. And then the third thing that we need is like this cross-privileged branch target injection. And so we want this syscall to lead to some code in the kernel where we can hijack the speculative control flow then. So the question is, how can we do that? And it turns out to be not very complicated. We just need to have some colliding code in user space that just branches into kernel memory, and that's of course, illegal. You cannot do that. It raises a page fault, but nonetheless, it will update the branch target buffer. So now we have these 3 requirements, so we can actually evaluate RETBLEED. So we did that on some Intel and AMD CPUs, and we can do it on on many of the AMD CPUs, however, not the Zen 3, and all of the Skylake CPUs are vulnerable, and the later ones are still have this RSB to BTB fallback, but they are protected by enhanced IBRS. On Intel we were able to leak arbitrary information at about 220 bytes per second. On AMD, about 4 kilobytes per second, and this was enough to find the ETC shadow and leak the password hashes of the system in acceptable amount of time. The mitigation is a bit of a headache, actually. So now they actually have to enable IBRS for the kernel because retpoline obviously didn't cut it. On AMD, we don't have IBRS, not in the same way. Yeah, we have it, but it's not going to work. So they have something that they call jump to ret, which which we explain briefly in our paper, and it's also written in their white paper if you're interested in that. Yeah, that is the end of this talk. So I can conclude with these 3 sentences. Returns can be predicted just like indirect branches on AMD and Intel systems. The BTB knows no privileged boundaries, and yeah, there are lots of vulnerable returns in the kernel. You can find the code and a blog post on this QR code. So thank you very much.